We've learned about the method of undetermined coefficients using the superposition approach. Here we'll consider another approach called the annihilator approach. So recall that a nth order linear differential equation with constant coefficients, of course we're still in the domain of constant coefficients, this still is the undetermined coefficients method. So we have this non-homogeneous differential equation with constant coefficients, and recall that this differential equation could be written in terms of operators. So we have this differential operator here, and on the right hand side we have g of x. In L, the differential operator could be written this way. Okay, so this expression here, where L is this, is equivalent to that expression there. Okay, they represent the same differential equation. Now, in general, linear differential operators do not commute. Okay, and what do I mean by that? So consider the differential operator here. L1 is equal to just the derivative d, and L2 is equal to x times d. Okay, so it has this coefficient of x. Now, of course, that would mean that we're not in the domain of constant coefficients, but it's just to, give an example. So if we act with L1 first on some function y and then L2, well then L1 is just the derivative, and L2 here is x times the derivative, and the derivative times the derivative here is d squared, so it's just the second derivative, and we get that expression there. That's what L2, L1 does when it acts on y. But on the other hand, let's switch the order. So this time we're going to act first with L2 and then L1. So here we'll have xd acting on y, but when we act with this differential operator d, we're going to have to apply the chain rule. And so here we'll get a 1 dy and then an x d dy, okay? And so these two expressions differ by this dy, okay, coming from the product rule. Now, on the other hand, if they have constant coefficients, they would commute, okay? And we express that in terms of a theorem. Linear differential operators with constant coefficients, okay, which is what we're considering here anyway for the method of undetermined coefficients, commute. That is, if L1 and L2 are differential operators with constant coefficients, L1, L2 is equal to L2, L1. Okay, you could switch the order. And also another note here, just as polynomials may be factored, linear differential operators with constant coefficients may be factored. And this is why I'm discussing the commutativity of differential operators, okay? It's because we're going to factor them. And it's natural then to ask, well, which factor should act first? It turns out it doesn't matter when they have constant coefficients because they commute. So let's look at some examples. Factor the differential operator that you see here, okay, of this differential equation. Well, this here is going to give you the d squared, 5y prime, that's just 5d, and then 6 here, and this should be 6y over here, okay? So we meant 6y there, and then this here is 2y, okay? That's a typo. Anyway, so we get this this operator, and if you just treat this as a polynomial, you could factor it out to d plus 3, d plus 2, and because operators commute, you could switch the order. Here's another differential equation, okay, and we get this linear operator. And notice that this 2x is not important, right? It doesn't do anything to the function y, Okay, so this linear operator acts on y, and that's why that doesn't factor in. Okay, that's not multiplied by some y there. And so we could factor this out, but we have here complex roots, okay, complex conjugate roots. And so we could then switch around the order, and we get this factoring. So notice also that in general, if we have conjugate complex roots, we could multiply the conjugate roots together, right? The linear factors with the conjugate roots there, and we end up with this linear operator. Just keep that in mind there. I thought it would be helpful to see that early on. All right, so let's consider this definition here of the annihilator. If L is a linear differential operator with constant coefficients and f is sufficiently differentiable function such that L acting on f is equal to 0, then L is said to be an annihilator of the function f, okay? So what does an annihilator do? It annihilates a function. And what does it mean to annihilate a function? That when you operate on it, you get 0, okay? So here are some common functions like that we'll be considering for the method of undetermined coefficients. You have a polynomial, xk, where k could be anywhere from 0 to n minus 1, okay, or linear sums of such terms, okay. Then dn will annihilate any xk as long as k is less than or equal to n minus 1, okay, greater than or equal to 0. That makes sense. So d to the fourth operating on x cubed, for example, or x squared, or x, or 1 will give you 0. D minus alpha to the n is the annihilator for an expression that looks like this, okay, where k again is between 0 and n minus 1 inclusive. For cosine beta x or sine beta x, this operator here annihilates it. You get 0 if you act on these with this annihilator. And for terms that you see here, where you have an exponential, polynomial, and a cosine, this annihilates it, okay? So that's important. And these n's really go into the multiplicity, right? So that's why this k is between n minus 1 and 0. That's why we need this n to ensure that this gets annihilated, okay? And a remark, for this method, we need the ai to be constants, the coefficients in the differential operator to be constant, and gx of the form of a polynomial, sine beta x, cosine beta x, exponential, or products and sums of these, okay? So this is still the method of undetermined coefficients, and we still have those restrictions. All right, find the differential operator that annihilates the following functions. What would annihilate this whole function? D to the fourth. Now we don't have to have d to the fourth plus d cubed. No, d to the fourth would, d to the fourth acting on 1 minus 5x squared plus 8x cubed is d to the fourth acting on 1. Or we could write it as a plus. You could also factor out the minus 5, that's fine. And each of these is 0. So here you're differentiating 4 times, so you're going to go down to 0. You're going to get a constant and then take the derivative of that and get 0. This is also 0, and that's 0. Okay? So it's 0. For 3, for B, D plus 3, and you could see that by operating, okay, D e to the minus 3x plus 3 e to the minus 3x. Well, the derivative of e to the negative 3x is negative 3 e to the negative 3x. And these cancel and you get 0. Okay? And likewise, you could follow the same method here, the same technique that I'm using, and just apply the operator on, say, this one here, operate on this, you'll get 0. And here we have, you know, alpha would have to equal minus 1, okay, and beta equal to 2. So this should be a minus 1 there, okay. That should be a minus. So alpha is equal to minus 1, and beta equals 2. And you just look at that annihilator here, okay. And these aren't being multiplied by this x that we would need for the multiplicities, and so this is just n equals 1. And so we have, if you just plug in this alpha and beta into here, you do get this operator. In general, annihilators are not unique. Thus, d plus 3 e to the minus 3x equals 0, and, well, we could just, d plus 2 acting on that 0 is also 0. I mean, in fact, you could multiply by other operators and still get 0, as long as that's 0, right? But in general, we're seeking annihilators of lowest order. Okay, so we're not trying to overcomplicate this and just add on superficial or trivial operators. Okay, so we want the lowest order. So here is a very important theorem for the annihilator method. Suppose L1 and L2 are linear differential operators with constant coefficients, and that L1 annihilates Y1 and L2 annihilates Y2. Then L1, L2 annihilates this, and of course, since these have constant coefficients, they commute, okay? And so we could have written it this way or that way. So what's the big idea here? The big idea is that if you have one operator that annihilates one function and another operator that annihilates another function, okay? And you take a linear sum of those two functions, okay? Some linear combination, c1y1 plus c2y2, okay? What would annihilate this linear combination? What would annihilate? It turns out this product of linear operators would annihilate it. You could see why from the proof here. So we have L1, L2 acting on this. So go ahead and distribute the L2. This is a linear operator, so you have that distributive property. You could pull out the C2 because it's also a linear operator acting here, and so L2 then acts on Y2 and annihilates it. Okay? And then you're left with this term here, which is L1, L2. Now L2 does not, we're not assuming L2 would annihilate Y1. L2 annihilates Y2, not Y1. But with commutation, you get that. So you could switch the order. And now L1 does annihilate Y1 and you get 0. Okay? So that's why we needed a product. It's not L1 plus L2, it's L1 times L2 that we need to annihilate the linear combination of y1 and y2. So that's very important. Now let's apply everything that we've learned above to solve this differential equation, and we're going to do it using the annihilator method, and at the same time we'll go step by step to understand it. So we're learning the annihilator method through an example. So here we have this differential equation. The corresponding linear differential operator is this, okay? D squared minus 3d, that's just coming from that. And of course, for the linear operator, we don't consider what gx. It needs to be multiplied by y or its derivative. And so our differential equation could be written in this form. So step 1 is to find the complementary solution yc of the associated homogeneous equation, okay? Well, the auxiliary equation here is going to be m squared minus 3m, okay? So this is just the left-hand side. The associated, don't forget, is you just assume a 0 there. And you get a root of 0 and a root of 3. And so the complementary function is c1 e to the 0x plus c2 e to the 3x, and you get that right there. So that's step 1, straightforward. Step 2, operate on both sides of the non-homogeneous equation that we started with a differential operator L bar, I call it here L bar, that annihilates the function g of x. Okay? So we need this L bar that would annihilate g of x. All right, here we have e to the 3x over here. Okay? The coefficient is not so important when you're annihilating. And so we have that d minus 3 e to the 3x is equal to 0. So that annihilates this term. Okay? But this is a sum of that term, okay? With 4 sine x. So we have what annihilates sine x? D squared plus 1 sine x annihilates sine x. Okay? And now, what do we do when we have a linear combination of those two? So we got what annihilates this, we got what annihilates that. Well, we go back to our theorem. Okay? What annihilates is the product. And so we take a product here of these two, d minus 3 with times d squared plus 1 annihilates this linear combination of those two. Okay? Thus choose L bar to be that product, because that's what would annihilate the whole right-hand side. And we then have that L bar acting on the original differential equation will be L bar g of x, right? Because Ly is just g of x. And we could substitute for g of x what it is, and we get 0, because we annihilates it, okay? Now this is super important, because notice something. You have an operator, right? A differential operator on the left-hand side, and you have 0. So we turned our non-homogeneous equation, we transformed it to a homogeneous equation in a sense, okay? And so now this is a homogeneous equation. Step 3, find the general solution of the higher order homogeneous differential equation. Of course, it's going to be higher order because we have differential operators in L bar. And so this here now is L bar L acting on y, and it's equal to 0 because it annihilated g of x as we saw above, and it's homogeneous. That's important. How do you solve a homogeneous equation? Well, you take the auxiliary equation. The auxiliary equation, and these are already factored, and the auxiliary equation corresponds to these differential operators. Okay, you could easily see that. um, because the auxiliary equation takes dn and gives you mn, right? D raised to the power n gives you m raised to the power n, and so we just have to change these d's to m's, and we get the auxiliary equation there. We then factor it out completely. We get this. We now get a repeated root, notice. Okay? This m minus 3 came from L bar. This m minus 3 came from the complementary function. Okay? And we then have the general solution to the homogeneous equation, this transformed homogeneous equation of this right here. Okay? And notice something. We didn't say anything about complementary functions, right? And that's what's nice with the annihilator method, is that you don't have to make that distinction between case 1 and case 2 that we looked at when we looked at the superposition approach, okay? Because we are getting this, we're transforming that non-homogeneous equation to a homogeneous equation, okay? Then we're getting, we don't have that same sort of problem. We then just get all of these factors for the homogeneous equation, okay? Now this is where the particular solution comes in. Delete from step 3 solution all those terms that are duplicated in the complementary solution YC, okay? So we have our initial complementary function there, okay? Not the complementary function for this transformed differential equation, okay? But the initial one. And so delete from step 3 the solution of all those terms that are duplicated in the complementary solution YC found in step 1. Form a linear combination YP of the terms that remain. This is the form of a particular solution of Ly g of x. So what is that saying? Look, for our solution to the homogeneous equation, general solution to the homogeneous equation, okay, that we got from this new differential equation, the higher order one, we see that these are in the complementary function, and they also show up here, okay, in the solution to the higher order differential homogeneous equation. Not associated not the associated homogeneous equation, but this new one. So what do we do? Because this is duplicated here, okay, we delete them. Okay, so we're going to delete these. And we now have, now what's left is the form of the particular solution, okay? So that gives us the form. We didn't have to worry about multiplying by x's as we've done with the superposition approach, okay? That kind of snuck in here by the multiplicity of a root for the homogeneous equation. Okay, that's where that snuck in. Okay, and we just changed the coefficients here just because we know we're going to try to fix these. Okay, we got the form of the particular solution, so there was no need. We could have just kept it C3, C4, C5, but just to be more consistent with what we've previously done, then we're going to change them to A, B, C. That's just a cosmetic change. And finally, substitute YP found in step 4 into the original differential equation, not this transformed one. Match coefficients of the various functions on each side of the equality and solve the results. So this is going to look very familiar, this step. So we have the left-hand side coming from the problem, okay, up here. And the right hand side is coming from taking our form and plugging it into the differential equation. So we get that. And now we just match coefficients. So this guy has to equal 8 because these are the coefficients in front of that same form. What's in front of the cosine x? Well, here is negative b minus 3c. Over here is 0. Okay, there's like a, if you will, a 0 cosine x. So that's where you're getting this here. And then this sine x, 3b minus c, needs to equal 4, and that's where you're getting that there. Okay, solve those three equations. It's a system. Just solve them, and you get a equals 8/3, b equals 6/5, and c equals negative 2/5. And so now you go back and plug them into your form, and you get this guy here. Okay? So this should look very familiar at this point, step 5. And finally, step 6, with the particular solution found in step 5, form the general solution. This also looks familiar. So here we have the complementary function, and here we have the particular function. And this gives us our general solution. Okay, and then this final step, step 7, if IVP, initial value problem, or boundary value problem even, apply the initial conditions or boundary conditions on the general solution. And here I write to emphasize not on YP or YC. Okay, you apply it to this whole thing. Okay, you would plug in the initial condition for this whole thing. On the left hand side you're given it, and on the right hand side you just plug in the point where you're given it. Okay, and you get that equality, and you could then solve for C1 and C2. The point here is to always remember that just because these don't have a constant on them, you still have to use them in order to fix these constants. Okay? So is this method very different than the superposition approach? So is the Annihilator approach really that different than the superposition approach for the undetermined coefficients? I would say not really, right? It spared us having to multiply by x's manually, but it snuck that step into getting the solution to the higher order homogeneous linear differential equation. Okay, we still had to manually delete the duplications. Okay, we still came in there and manually deleted the duplications that you see there. All right, we had to do that by hand. So they're really quite similar. I wouldn't say there's any seismic shift between the two, but you know, maybe some people have a preference for one rather than the other.